Data analysis in particle physics can be much more sophisticated than we looked before, and we'll talk about it at the third lecture in more details. But for the moment, we have to keep in mind that all measurements physicists do come with uncertainty estimation. For example, tracking algorithm that finds muon from the previous exercise should be evaluated somehow before we can pass some data through it. And thanks to standard model, we can simulate very precise image of particles flying around the detector. At this slide, you see the second half of data analysis, the second part of data analysis. So two axes like processing time and amount of information that is or density of information that is available in a single object, and there is a bottom of this plot that shows the real data, the raw data, and if you follow this parabola to the right, you follow the path that we described previously from raw information that detector records. We collect reconstructed points, then track segments, then track candidates, then vertices, and then the whole decays of certain kind. But at the same time, there are very strong software and models that can be used to simulate every step that happens on the detector level and subatomic level. Actually, there are event generators that produce signal-like patterns, and then you can estimate what kind of response you can get from the detector, what would be the energy deposition if you see something like the signal. And then you can go down the level of the abstraction until the raw data, and ideally the representation of the simulated event and representation of a real event should be the same. Of course, it is not the case like by 100%, because some processes are very difficult to estimate and simulate, but still the picture shows that there is a very great deal of software and efforts put into simulation of the physics. So all the algorithms, for example, tracking or triggers, are evaluated on the simulated data. And it is very important problem efficiently and accurately simulate physical process. At the moment, it takes roughly 80% of computational power of computational grid that CERN uses for data processing. And roughly it is proportional to the amount of data you're going to collect. So there is a big problem when LHC is going to switch into high luminosity mode, when generation of data will be tens much larger. At this slide, I've just presented traditional packages that are used for simulation of various aspects of particle interaction, like neutrino interaction, generic simulator for processes called Pythia, and GEANT that is used for simulation of particles interacting with matter. It's not only used for particle physics, but it is applied to a variety of different cases. But at the link below you can find much more examples of such software. And with this regard, I would like to mention two more additional challenges that are relevant from the perspective of our course that focuses on machine learning. So the first one is speed up of simulation that can take advantage of generative models based on, for example, neural networks that can work much faster than traditional simulators, and tuning of simulator parameters to find the best combination of parameters that make simulator produce the most accurate and realistic pictures. So those simulators are being used outside of CERN already, for example in medicine and space technologies, and there are plenitude of other technologies that has been produced as a byproduct of research at CERN. Those cover, of course, Internet and World Wide Web, myonography, aerospace and cryogenics, ultravacuum techniques, medicine, of course, based on ion radiotherapy and hadron therapy. So there is a whole site that is dedicated to technologies that has been born at CERN and now being applied to everyday life of humanity. I'd like to conclude this lecture and to stress once again what is important from our perspective here. The first thing is LHC is a massive sub-elementary scale microscope, and it allows to look into a fascinating research area that no other tool can give access to. There is a substantial theoretical foundation that offers pretty good explanation of what we have seen so far on particle level physics, but it is not complete yet. Some pretty fascinating phenomena are awaiting for clarification, and LHC allows to probe for theory extensions and to see which theory gives better explanation for those. At the same time, there are plenty of machine learning challenges that include data analysis, surrogate model optimization, and experiment design that are waiting for minds and talents of data scientists to be solved. I hope that homework and challenges we prepared for this course will keep you engaged and allow you to get the feeling how machine learning can improve things at fundamental research.